Thank you. So thank you everybody to be here today. For me, it's quite a special session. As we promised to the organization, and it's a pleasure. First, I will continue speaking, if this is working somehow. No, that's the way. Yeah. Okay. So I'm going to continue speaking about Professor Kowalski a little more. When he left us in 2021, we were speaking about him, remembering him, in particular Zdeněk Duxe and myself, who are together with Vladimira, the 3 PhD students, officials one. Of course, he has many more, but in an official way. As Zdeněk showed you, he has many interesting results, many achievements, many papers, many collaborators, many goals in his life. But we also know him, what is behind that. And for us, one of the things that we most value about him is how he get that achievement. Not only the achievement itself, but the way he obtained that. So, okay, this is not working with me today. Yeah, there is a really great part of Professor Kowalski, the human one. So we decide we have to write something because he have the good luck we can celebrate with him many birthday and party in his honor. So must be write something about he as a human, and in particular as advisor, because this is something that we know. So it is published here in this paper, and it's published by Zdeněk Duxe and myself. I would like to speak a little about it, what is inside, complementing the information of the previous talk. So he have many collaborators, he know a lot of person. And one of the things I always asking in my stays in Prague when I was working with him was, and also special by Zdeněk, was how he was able to meet too many people, different cultures, different religions, different personalities, always be okay with most of them, cooperating and making advance with them. How that was able. So we asked him, and that is, okay, this is what he said to us. He said to us that he is not choosing his friend. He leave it of them to choose him. That means for us that he is open to every person that needs him in any moment. And not only in a mathematical way, but also in a personal way. Because there are many, many examples, but just to say one, when it was the Yugoslavian war, there were many Serbian students in Prague, and he was taking care of his needs. That was before I arrived there to the life. So for us, this was important. So let me complement that sentence by this for us, that everyone who choose him as a friend have not regretted. So we have been really great about that. Really. So instead to speak about many students that maybe I don't know many of them, because I maybe the last one to arrive to his life, we decide to write this little paper with our experience. So let me just put some sentence of the paper so we can record in him a little. He as his human part, okay, as well as the way he used to work. Because now for me it had been really important when you start to become an advisor, then you think how to do that. And when you have a good example, you know, the things became easier. Yeah. So from Zdenyedu's part, I had put here some sentence from the paper. He can show us how he was as professor, because he had the good luck to Professor Kowalski give lecture to him about Riemannian geometry, differential geometry in Prague. So he told me that he liked this topic, but in particular the prepared lectures, the tutorials, and that make him to learn a lot, even appreciate more the topics. Yeah. So something that he learned about Professor Kowalski, that he was really separate every task. If you want to prove something, demonstrate something, he really make partial step, and every step have to be really justified. It's not going to with him by here, from here to here. It's going to be, oh, it's easy. No, let's go to see it. There is no any minimum step that jumps. This is not possible with him. So that is maybe his reason to choose him as supervisor, even if he won't be an easy in his period. In that time, he even didn't know if it will be a good idea, but I think it was at the end. So, another experience that he shared with people in the paper is when he was helping him. Professor Kowalski was editor-in-chief of Differential Geometry and Application Journal, so he was helping him as editorial assistant. So he was really witnessing how he worked. He worked in a really systematical and careful work with every paper that was received there, giving relevant report, seriously justifies decision, and so on. I subscribe this. When I was in Prague and in my stay, I have to be in his office. That was the possibility, and I saw him how he really worked like this. So it was great and amazing to have the opportunity somehow. So maybe we think that this could be the reason that when he was with a conference and you are with the conference with him, you feel like the maximal respect from everybody there, and in general of the mathematical community, and that was an honor somehow. So, but the work he do is not only focusing in the formal accuracy or the punctuality, but he also focus in help a starting mathematician. When he recites some word from an starting one, maybe he have to reject it, but with advice and revisions, and helping them to achieve the level for publication in a journal of high level, like he wanted to be differential geometry and its application. So that was really care for you. And in fact, in particular in the DGI conference where we are today, and in the Riemannian section where we are today, he was really making big efforts to give at least 10 minutes for the younger mathematician that he considered they could say something, to give some little talk about the result, to promote the youngers here. Okay, I was one of that younger mathematician that have the opportunity of that 10-minute presentations. From my side in the paper, I can say that I met Professor Kowalski when I was doing my master PhD in Spain. So I was in Spain doing my master. There I was guided by Professor Naveira. And he pushed me to work about generalized symmetric spaces. The topic was, Professor Kowalski was really an expert in Euro, everybody knows. So I worked in emails with mathematical questions and so on that he always answered in a proper way. So at the end, he became one of the person of the committee of my master PhD and visit us to Spain to evaluate the master PhD. After that, that was the same year, there was the conference, and Professor Kowalski told me I have to give this 10 minutes talk in this section, and I was so crazy because it was my first year, my first international conference. Everything was like a lottery there, and I was really scared, but looking forward to use the opportunity. So, but he not only accepted me to give 10 minutes talk in this section, but also accepted me to be visiting him at least 3 months to Charles University. So I came to the conference and continue until Christmas here, in Prague in that time, okay? So I was so glad, and I started to prepare my visit, but unexpectedly, he started to prepare also the visit. That was, I think, who made him really different. I received an email with many questions about my needs to have a successful experience in Prague. Not only mathematical way, but also in my personal way, or in my hobbies. Or he really wanted I feel fine there with the little things. If there is no a big office for me, of course, I never asked about that, but just he left me a space in his office or wherever to feel fine. At the beginning, it was like a shock, but then I answered the questions as good as I couldn't, and I'm really glad about that, because after that, Professor Kowalski and also his family made me feel really comfortable in Prague, in the sense that I was able to relax doing research. You know that at the beginning when you are a PhD student, you are always, I have to get a PhD because then I don't have work and so on and so on, but he made me feel comfortable. I discovered this point of, and you can enjoy doing research, yeah? So they became my Prague family. At the end, Professor Kowalski also became my second supervisor. I'm really glad of both of them. My Prague stays continuing also after finish my PhD. Since that year, I think there is no any year I haven't visited him in Prague. So, but every time with him was shared moments about mathematics, but also about the life. So was the daily lunch times where we discuss open problems, and so that were always telling me at the end, but please don't focus this now. Focus in your PhD. These open problems are for you where you finish PhD or for some other person. And yeah, taking care in that sense. The best moments for me were when before he go home at the end of the day, if he has some little time, he can have some little time with me. He tried to solve my mathematical questions, propose me changes, of course, but I never feel with her like, oh, he's going to say me, I have done this really wrongly or something. No, he made me changes with rigorosity, with precision, and also with patience and with care, and every level, and I'm really glad about that. So, as an anecdote, I don't know how to say that in English, maybe the same word. I will never forget the day when he allowed me to refer to him as Oldřich. He told me we had been know each other enough time to call him by his name and not necessarily call him every day, every moment, Professor Kowalski, I need something, or whatever. So, but he put me some condition that I have to be able to pronounce perfectly his name. I'm not sure if I'm able still now, but I swear he was patient with me, and he was helping me with a new task, and we really enjoy a lot. That moments, yeah, between many other. So just as finishing, I think we both want to thank Professor Kowalski, wherever it was. Thank you, because very much for being part of our lives, and also to letting us be a part of his life. Yeah. Okay, now I need mathematics. Okay. My life have it changing a lot. So I started, yes, in that some result that Steklov to present before. I found about affine connection, that three spaces. about Willi-Einstein spaces. I have worked also starting with generalized symmetric. I also work in the classification but naturally reducted space in dimension C that Professor Kowalski has taught me and say, no, first PSD, later classification. So, but the life continued and I arrived to this. My life bring me here and also glad. And I would like to try to speak about the last result we are working in because it's really not published and we are still improving. So I hope you're enjoying it a little as I used to do. So my focus here now we are working is in trying to establish the problems of the mixed Steklov problem and try to find bound for the eigenvalues of these kind of problems. It's in dimension 2 and it's in cooperation with Emily Dryden, with Caroline Gordon, with Asma Hassanezad, Ali Ray and Elizabeth Stanhope. We have been working some years, we have already the paper, and this last one is the one what I wanted to speak about, just a little result inside the paper. So, as you see the title of the paper, the main topic here and the clue here is the hidden symmetry that we can use. It's a lot of things know about Steklov problem, but we are using everything know about Steklov problem to use symmetries and to bring results to mix eigenvalues problems. So I will go step by step, so let me focus what Steklov problem is, and I think I'm going to be really fast. So the Steklov problem is quite old, was posed by Steklov, and is taken in a Riemannian manifold which is compact, with not empty Lipschitz boundary. So if you allow me, this Lipschitz boundary condition, I'm not going to say what it is in this moment. Just let me pass a little more in the talk and we will develop a little more slices about that later. So the point is to find the functions which be harmonic on the compact Riemannian manifold, but in the way that such smooth function, the partial derivative in the direction of the normal unit vector, be proportional to the functions with some scalar. This scalar is what is called Steklov spectrum, and there is an infinite series, discrete infinite series of that spectrum. So something that hides the symmetry here is the possibility to consider this a compact Riemannian manifold with, of course, no Lipschitz boundary, and consider a discrete group that is acting on it. So when we have this compact Riemannian manifold and we have this gamma invariant metric on it, we have this quotient surface with boundary where one metric is the pullback to the other, but it's gamma invariant. So yes, for example, I see. Let's see if this works. Okay. So when we do this, we can you can think, for example, in the S1, for example, and you make the action of a symmetry here, then what you get is exactly something like that, okay? So that will be the quotient and the other one. When we have the quotient, this part here is what we call the boundary. So this is the boundary of the quotient, only one. When here the boundary is all this. Yeah, that is going to be important later because we are going to combine Steklov with mixed Steklov, and this is important part there. On the other hand, something important is when we have this kind of quotient, as you here see, we can have different kind of what we call boundaries on orbifold. So this, when you think in this half, this boundary is type 2, what we call type 2, and when we have a boundary in that sense, it's what we call type 1. Okay, so I'm going to do this because I'm not sure what's happened. Okay. So the important here is when you have a quotient, then you have the Steklov of that quotient the Steklov spectrum inside the other one spectrum. So to get one from the other, you have to choose the eigenvalues were corresponding with the gamma invariant eigenfunctions. Okay. Ahora que Ana no va. Okay, for example, if you take the dx, then you have the Steklov eigenvalues are this one, and the eigenfunctions are this cosinus and sinus. So when you make quotient the Euclidean disk by a reflection, then what you get is this Steklov eigenvalues of the quotient, and the eigenfunction, we just keep it the one which are invariant under the reflection. Okay, why I say this is because I wanted to put out exactly what kind of upper bounds are we interested in. So our previous paper was about orbifolds, and orbifolds in dimension 2 can be seen always as quotient spaces, global quotient of a surface with boundary but the action of a discrete group. So what we got before was some kind of upper bounds for the weighted Steklov eigenvalues in this sense, where depend on positive universal constant. This was in arbitrary dimension, only dimension 2. If you see these eigenvalues here, they are depending only on the topological information of the compact Riemannian orbit surface we are interested in. The Euler characteristic, R is the number of type 1 boundary components, the one of the circle, and S is the time 2 boundary components. So this kind of result are we interested to generalize now, but not to this Steklov problem on quotient, but to the mixed ones. So something important to interrelate our problems, because we go for the mix, we wanted to use the Steklov information in the problems to the mixed one, is to go to study the weighted Steklov problem. So the first is to introduce a non-negative wave, this one row here, a non-negative wave with support, with some support, that we will denote by this. But this, you can think that it's going to be the boundary of the domain which we are posing there, the Steklov condition. The Steklov condition is this one here. So now the Steklov condition is just changing by these normal derivatives in the direction of the eigenfunction, in the direction of sigma rho and this u. Okay? And of course, as before, we have the discrete infinite spectrum here. Another important tool is when we are in a weighted Steklov problem, we can make conformal changes of the metric. This is going to be a really special clue and important. It's simple, but really important. For example, if we make a conformal chain of the metric in the domain, yeah, but in the, let me call Steklov boundary, the metric is not changing, then we are not changing the spectrum. So we can make conformal changes of the metric, modifying as we want it, if the Steklov part we are not touching it. So what is now about this weighted eigenvalues upper bound? So Wien's thought proof was working in upper bounds of the first weighted Steklov eigenvalues, and he get that this weighted eigenvalues is always less or equal to 2 pi, and moreover the 2 pi is attained when we take the weight equal 1 and the omega is exactly the Euclidean disk. So that cannot be proved, and it's there, and it's quite result. I think, I haven't said, but this is the length, the weighted length of the boundary of omega. Several years later, Herzpen and Schiffer generalized the result to this sigma k, to the others eigenvalues. And in 2010, Giroua and Porterovich proved the sharpness of this quality here. Yeah. Now we know even more. We know even more that this is a strict sky is greater than 1, but okay, I haven't incorporated here yet. This is more or less what is known about this equality. So we wanted to improve this and to work here in the mixed problems. Yeah. But for that, we will need these results. So one key result is did by Bukur and Ahor. Under some hypothesis, I'm not going to say that because with this time, I need at least 4 slices for the hypothesis. What one can do is that if you have some domains that tend to converge to another domain and some weighted that tend under some condition go to the another weighted, then the eigenvalues will also tend to the eigenvalues. So this is where we wanted to somehow quote, but with this we can be, for example, working, approximating a domain with some other domain with have, for example, a smooth boundary instead of listed boundary, or some information that we can calculate here and not here. Yeah. So for the hypothesis, we need to understand what is listed boundary when we say that we have a domain with listed boundary, and that have to be with a special chart. I see the time, so I'm going to be a little, if you doesn't matter. So let's say that listed boundary is you have in every point of the boundary a special chart with some characteristic that have to be with the listed constants of the function that relay in the domain you are working in with the chart that the coordinate you are working. Yeah. Yes, after that, we need regularization and uniformization Lipschitz boundaries, which mean that instead of every point take a special chart which will have its own Lipschitz constants, we wanted that the same Lipschitz constant somehow work properly for every point of the boundary. Yeah, let me resume that way. So, after that, we wanted to introduce is a known concept that when a sequence of domain converge uniformly to a domain, because this is something we need to establish later, create domains that converge uniformly. So these are the conditions that we need to this uniformly conversion. And finally, one can put really the Bukur-Nahon result that I speak before, and these are all the hypotheses one needs to be able to apply it, that it will be relevant for us. So we need this uniformly convergent of the domains, have quotation of the weighted, and when we consider the measure be weak star convergent in the measure sense. So in that way, we can create domains that converge to another, and that we know that the Steklov spectrum it's maintained somehow. So now let me arrive to mixed Steklov problem. The difference, let me start, we're introducing this paper by Hers and Payne. And an Steklov-Neumann problem, we are going to speak about 2 problems, Steklov-Neumann and Steklov-Dirichlet. So the Steklov-Neumann problem, we will be interested in the Steklov-Neumann spectrum, that will be this constant here, which satisfy that if you see we have a domain and have the boundary, we can divide the boundary in 2 parts. If you remember the half this, so in the half this I told you I have this part that is the Steklov boundary, so the part that I didn't say anything before will be the part where this condition is a time, okay? So, and here we also know about the discrete theory of the spectrum. Yeah? This Steklov-Neumann problem is really somehow important because we can relate with the Steklov before. we take something simple is take rho equal 1 on the Steklov boundary and rho equals 0 on the Neumann one, for example. Or another way we can do that is to take some, make a conformal chain of the metric, that we can do that without the spectrum. So making a conformal chain of the metric where we involve the way, we can interrelate the weighted Steklov problem, the spectrum of the weighted Steklov problem, with the spectrum of the Steklov-Neumann problem. So we can interrelate Steklov-Neumann with weighted Steklov. So due to Buchurna-Horn, this approximation that domain can be applied before in the weighted Steklov case, now we have been adapting the proof by no difficult one, so we can apply Buchurna-Horn on the spectrum in the Steklov-Neumann problem. Yeah. And now the Steklov-Dirichlet problem. The Steklov-Dirichlet problem is similar to the previous one, but now we change in that other part that just we are allowing that the function to be 0. If we want to think in a physical way, for example, thinking in thermodynamics, if you think you have a contain and you want to study thermodynamics of the contain, so instead you make a slice of the contain. So the upper part, yeah, where the hot is going out, that part will be the Steklov part of the domain, and the contain, literally the contain is will be Dirichlet if we are forcing that the hot in the boundary be 0, or will be Dirichlet if we are assuming that that contain have the walls insulated. Yeah, for example. So it's going to be important because we are going to have bounds for Steklov-Dirichlet and Steklov-Neumann at the same time to know how they can be related. The Steklov-Neumann spectrum, it's always less the k eigenvalue is always less or equal to the k plus 1 eigenvalue of the Steklov-Dirichlet, so we can relate one with the other. And the notation we use here is if we are going to take a complete Riemannian surface, a simply connected bounded domain with no intelligent boundary, a non-negative wave, we will denote the support of the wave by this notation here that I'm namely Steklov boundary, that we are going to assume is, of course, is not 0, else we don't have even any problem here. The boundary is going to be divided in two parts. The Steklov one will be always there, and the other one could be Neumann or Dirichlet. And for simplicity, in our result, we will assume that the weight is equal to 1, although the results are also valid if that's not the case. So, to establish notation, let me D be a collection of triplets, and every triplet it's going to be formed by the domain, the Steklov boundary, and the boundary that the star boundary, we will call that could be Neumann or Dirichlet. I say that? Yeah. So what we have get it here is that in that case, if we have a complete Riemannian surface and we have a triplet, which means we have a domain with some boundary condition in it, then what we can say about the weighted Neumann eigenvalue or the weighted Dirichlet eigenvalue is that the minimum of then is always less or equal to 2k minus 1 times p. So that will be improved. We have added this to the results, to the previous somehow result. Another thing we have been done here is we have proved the sharpness of this inequality in the sense that we can create domains that the weighted eigenvalues tend to 2k minus 1p. So that way that is sharp. how much time you give me, because I start... Okay, I have my 40 minutes also? Okay. Oh, thank you. So then what it's remained to me that is trying to show you how the proof's going, because I think it's a nicer one. For the proof, we need two important lemmas. One of them is the domain monotonicity, what we call it is. I mean is that if we have two triplets, let's say we have two triplets in the way that one domain is inside of another domain, because later in the proof we need a succession of domain, one inside of the other, just to be controlling the spectrum in that sense. But we need one inside of the other, but the Steklov boundary cannot be moved. That it has to be fixed. Like when we make a conformal chain of the metric must be exactly the same in that part. Yeah? So in that way, with this domain monotonicity, what we know is that the spectrum of the mix with Steklov-Dirichlet of omega 1 is always bigger than the omega 2, but in the Neumann part, it's just in the opposite direction. Yeah? So this is somehow well known by people in the area, but we couldn't find really a proof. But we found a proof in a really modern paper, yeah, by, I think is, I don't remember this moment. Okay, I will tell you later if you wish. So we found a proof when they are working this with Euclidean space. Yeah, so the proof can be adapted to a complete Riemannian surface, so it's really working. And the other lemma we need is the... Oh, God. Okay, the convergence between the inequalities. This is really a strong one, the center part of the proof. So if we take a complete Riemannian surface and then we take a triplet, means this is what we are really interested to know and quote the spectrum there. So if we suppose that there is a sequence of domains, and this sequence of domains satisfy these properties, then we can take this quote, but the domain we are interested in. Yeah? So which are the properties? The properties is at these two domains, first, we have that quotation for them, so we have to prove that in that set domains. The sequence converges to omega uniformly in the sense previously done. Of course, all of them are inside of omega, but, and this is really important, the Steklov part doesn't move and is always fixed. Yeah. So with these two results, the convergence between inequalities, for proving that, we need Buchurna-Hahn for this part here that tends to this part here. This is why we need to interrelate with weight, the Steklov problem, and so on. For control Dirichlet, mixed Dirichlet is where we really need this inequality there. So with that too, this lemma appear. Okay, so now to do, this is a really sketch of the theorem proof. I hope can be understanding. We have divided the proof in three cases. The general one, that will be the last one, and case one, that is going to start to present it, and of course, and a case two. This picture, half of the cases put together there. So I will try to explain a little this. This that you are seeing there, okay, let me, oh, how can I draw here? Okay, so imagine we have a, okay, let me do something like that. And now I'm going to take this. So imagine we have something like that, the point, another one, let's see, from here, okay? This will be what we call this boundary, with the star boundary, and that will be the Steklov boundary, yeah? And that is what I'm putting here in red, will be part, it's part of the domain. The domain is, could be bigger here. So the first inequality, the first case, we are going to think here that that part, the green part, is polygonal in the sense that is piecewise geodesic. Also that satisfy the double Lipschitz conditions and point P and Q. Okay, this double Lipschitz condition is something we have to incorporate here. So let me explain you what is it, because it's in our paper. That is the P. This is a point where both boundary converge. And Q will be the other point where, of course, if we continue the green one and we continue the blue one, will be joining again in some point. So that will be the other point. We say that they have the double Lipschitz condition when we can find a neighbor here, yeah, small enough, so that using the exponential normal coordinate. So here you are seeing here is the tangent space of point P, okay, of manifold, where, let's say that. Here we are interrelating the exponential here, of course, and you have the logarithms in the other way. So we need a U small enough such that, and now let me go. This Steklov path go here. That will be the representation there. And now we have the green one. With the green one is where we are going to be playing in the different cases. So the first case here, we are thinking that this domain satisfies the double Lipschitz condition when the green one goes here. So it's here, okay? Forget the other part of the draw. So we need here, so we are thinking in the image of, if we consider this part here is small enough, okay? This will be the log of U intersect with omega, small enough so that this green part for an angle less than pi, is in the other part, this line here, so this part is in this quadrant here, okay? Not here, because else we lose the Lipschitz condition that have to be satisfied all the other properties. So we need to be here. So when we have it there, we have the double Lipschitz condition. If we have this, then after that, what we do, that is to double this space. When we double, we get a surface, not inside the plane, a surface itself. This surface, due to this piecewise geodesic, we can assume also making a conformal chain of the metric that this is geodesic. So when we double, we don't get holes, else we lose the topology property. And when we get that surface, it's a surface with a boundary, we have the Steklov property where we can use all the machinery for the Steklov problem there. So we can double, go there, go Steklov, applying the machinery, and then bring it back with these reflections and bring the information there. With that, we get the result in that case. So now let me see how. Oh, now is everything here. Okay. Okay, the second case, I'm finishing, okay? Just finishing really. Yeah, the second case is where we have to create, and let me see here. Yes, appear the, well, the second case where we have to do, due to every domain with this line became here, it's really a domain where we can control and we can quote. What we do is the line became in this part is to make adjustment and create subdomains taking part of this line and part, no, okay, wow. Okay, part of this line, and that's, so we are making subdomains approximating to the domain where we want it to arrive. And then proving that that's subdomains arrive and create well the properties and the curve, we can be obtain the results for the previous case that was here, that is the case one, but we are not assuming the double Lipschitz conditions. Okay, so I'm losing that property now. We still need that polygonal assumption, so the general case just is construct a sequence where the polygonal assumption take the general where the polygonal assumption is not there. So we construct a sequence of polygonal, of subdomain we have the polygonal assumption, and for each of that polygonal we construct the sequence that have also the latest one. So, and with this we are able to prove, and thank you. I'm going to try to erase this. Thank you, I have finished here.